In this video, we are going to talk about the product rule of integration. Just like how we had a product rule of differentiation, we are going to talk about a product rule of integration. And the product rule is called integration by parts. But before we get into integration by parts, I'd like to first show you how the product rule of integration is related to the product rule of differentiation. So we know from our course in differential calculus, calculus 1, if we was to take the derivative of a product of two functions, we would get this. But what if we had this and we was trying to get the functions, the two functions that got us this? How do we go about it? Well, it makes sense to take the antiderivative of this derivative with respect to x of this side to get us this side. But since this is an equation, whatever we do to one side, we must do it to the other side. So we will also take the antiderivative of this side with respect to x. So on this side, we see the dx's cancels. And we're left with the integral of d f of x gx is equal to the integral of f of x, f prime of x, g of x, plus f of x, g prime of x, dx. But we know from the fundamental theorem of calculus that an integral of a derivative, so we had a function q of x, is equal to just q of x. So knowing that, we see that the integral of the derivative of f of x g of x is just f of x g of x. So we can go ahead and say, well, this is just f of x g of x equal, and we could separate these, the integral of f prime of x g of x dx plus the integral of f of x g of x dx, g prime of x dx. And we see this is the antiderivative of this. So if we had a function said integral of f prime of x g of x, right? So if we was given a function like this, this is equal to f of x g of x minus the integral of f of x g prime of x dx. So it's like we brought this to this side, brought this to this side, multiply both sides by -1, and we got that. This was for this one. See, use a different color. Well, what if we was given an integral? So this is 1. This is another way of writing the equation. So if we was given f of x g prime of x. Sorry, I forgot to put the dx. dx. Well, this is also equal to, f of x, g of x, we're just rearranging the equation, minus the integral of f prime of x g of x dx. So these are the two ways we can represent the partial integration equation. So these are the two ways we can represent the partial integration equation. So this tells us that if we had some function, if it was given two functions as a product, we could choose which function to consider the derivative. So we could either say, okay, f of x is the derivative of something, and we will still get the same result. Or we could say g of x is the derivative of something, and we will still get the same result. So this is pretty much the equation for integration by parts. And if we see here, this is the equation. This is how you might see that equation in your book or any other books. So it's customary to use to write the general equation as f of x g prime of x dx equals to f of x g of x minus the integral of f prime of x g of x dx. So we can do substitution. Say u is equal to f of x, which is this, and we have u. We have dv is equal to g prime of x, which is this. Then we have dv is equal to uv, because u is f of x and v is dv, so v must be, if dv is g prime of x, then v must be g of x. So we have v, which is the g of x and f of x, minus, so again we have v is just g of x, which is this, and we have f prime of x. F prime of x is just f prime du is just f prime of x, which is this and this. So it's the derivative of u. And that is pretty much the integration by parts, the equation for integration by parts. So let's look at a problem. So if we had a problem that said find the integral of the natural log of x dx, and this is our equation. It's always helpful to write the equation everywhere we go where we have a problem, to write the equation so we have something to reference. So that is our equation. And we have, these are the substitution that was made. And if we was to solve this problem, how do we go about it? Well, we do not know the integral of the natural log of x yet. But we do know the derivative of the natural log of x with respect to x is 1 over x. And we know the antiderivative of 1 over x dx is equal to the natural log of x. So we do know these. So this must be, so we know ln of x is an antiderivative of something, not a derivative of something. So it would be helpful if we represent it as f of x, which is an antiderivative of something. So we could write, say, f of x equal u equal ln of x. And we can have du equals f prime of x equals 1 over x. We have the first part. We have u and we have du. So what is v? Well, we see we're just left with dv and v. We're left with dv and v. So if we was to take the integral, say if we was to take the integral of dv, we should be able to get v, right? That's pretty straightforward. So, I'm sorry, we have dx. Dx is the dv in our equation. So we dealt with the ln of x. This is the ln of x. We have it here, which is the u. We are left with dv. So if we was to take the integral of dx, we would get x. This tells us that dv is equal to dx, and v is equal to x. So we could just, with all this knowledge we have, we could just substitute everything into our equation. So we could write something like that. So this, so this is equal to u, and we know u is the natural log of x. It's ln of x. And we know v, we're following this equation. We know v is equal to x. So we have the natural log of x times x minus the integral of v, which is x. So v is x, and du is f prime of x, which is 1 over x, times 1 over x dx. So this tells us that, well, this is also equal to the natural log. We just bring the x to the back. We have x natural log of x minus, well, we have x, there's two x's here, one at the bottom and one at the top, so these cancels, and we just have the integral of dx. And this tells us that our answer should be something of the form x ln of x minus the antiderivative of dx. But we already saw the antiderivative of dx is just x minus x plus our constant c. And that is our solution. So we see the integral of the natural log of x is just x ln of x minus x plus c. This is the indefinite integral. And this is the solution to this problem using integration by parts. So as you might have noticed, the hardest part of this was setting up our u's, setting up this part. But everything else was just straightforward in substitution. So let's take a look at another problem. So what if we was given a problem like this, say we actually had two functions. So what do we make our u and what do we make our dv and our v? Well, we see e to the x, the derivative of e to the x is just e to the x. So in choosing your u and your dv, we want to choose u and dv that are going to simplify the problem. So if we were to pick, say, u equals e to the t, right? And dv equals sine of t. So this tells us that sine of t is the derivative of something, right? And e to the t is an antiderivative of something. So we pick those two, and this tells us that du must be equal to e to the t, because the derivative of e to the x or e to the t is just e to the t. And this tells us that the antiderivative of dv, the antiderivative of sine of t with respect to t is equal to the negative cosine of t. So we have everything we need. We have our u, we have our dv, we have our du, and we have our v. This is the v. Which is that this is v, the antiderivative of dv. So having all this, all we have to do is just substitute that into our equation. So we have this is equal to uv. So we know u is e to the t. uv is the negative cosine, so we put the negative here and we write cosine of t. And we have minus the integral of v, which is negative cosine of t. Since it's a negative cosine, it's changed to a plus. We have cosine of t times du. We know du is just e to the t. It's just e to the t. So we write e to the t dt. So it's like we took the derivative of u with respect to t and we multiply both sides by dt. So we get another product. So if we do this, if we pause this for a second, right? Pause this. If we were to pause this for a second and deal with this product that we have here, we'll see that, well, the integral of cosine of t times e to the t dt is equal, we follow the same pattern. So we could do u2, or we could just mentally do it using our equation here. So we could say, okay, cosine of t must be the derivative of something, so we have to take the antiderivative. So let's just go. So we have u2 equals to e to the t, right? And then we have du2 equal to e to the t dt. And then we have dv is equal to cosine of t dt. And we have v equals the antiderivative of cosine of t is just the sine of t. Sine of t. And we can just use our equation and just substitute everything. So we have v and u. So we need u and v. So we have e to the t sine of t minus the integral of u v du. So we have our v, we have our du. Integral of sine of t e to the t dt. How about I get rid of this? dt. Jeez. dt. So just looking at this problem, but we can just go ahead and substitute this value into this because it is equal. So we can write our problem as I need a different color. We have the integral of e to the t sine of t dt is equal to e to the t, this part, is just, we're writing this part now, is equal to negative e to the t cosine of t plus this, which is this, e to the t sine of t minus the integral of sine of t e to the t dt. Yeah, I know you might be thinking, well, isn't this exactly where we started? Like, we haven't made any progress at all. We just went in a circle, but this is very acceptable. This is the same as this. This is acceptable, so we can just solve. We could add this to both sides, right? If we add this to both sides, we get 2 times the integral of e to the t, because we get 2 integral sine of t, we just added together, and we just get 2 e to the t sine of t dt is equal to negative e to the t cosine of t plus e to the t sine of t. So we can go ahead and divide both sides by 2. And then we have the integral of e to the t sine of t dt is equal minus 1/2 times e minus 1/2 e to the t times cosine of t plus sine of t. And that is our answer.